Hello, welcome to the today's session, Design of Reinforcement Concrete. Our course outcome is design and detailing of lintel problems. In earlier sessions, we were discussed on design procedures and how to design steps for the design of lintels. As we seen in the earlier class, in design of lintels, the major changes with compared with the singly reinforced beam is the load calculation, because in most of the lintels which is not connected with the chaja will have only a dead loads, that too the wall coming over it. So once if we are able to understand how to how to consider the load from the wall, you can easily design the lintel. So today we are going to discuss about the problems on lintel, that too first case, that is arching action. Arching action we're going to discuss today. So problem. So the width of the opening is 2.4 meter. Height of the brick wall above the lintel is 3 meter. The thickness of the wall is 230 mm, and the bearing width of the wall is also 230 mm. Then concrete we are adopting here M20 and steel as 415 steel. And weight of the concrete, that is the density of the concrete, is 25 kilonewton per meter cube, and density of the brick wall or weight of the brick wall is 19.2 kilonewton per meter cube. And once if you design, you should also sketch the reinforcement details. So this is the what given in the problem, that is the length. This is the opening length, which is having a length equal to, or opening you may call as a 2.4 meter, 2400 mm. And height of the wall 3 meter. This is the height of the wall for the opening, 3 meter. And the T is the thickness of the wall. That is nothing but the width of the wall, that is equal to 230 mm. And bearing also, as per the problem, 230 mm. And these are the other remaining data regarding the material is used and the density of the concrete and brick wall. So as the first step, we need to assume the effective depth. So effective depth can be obtained either with the help of uh, span to depth ratio, L by D ratio. So by using this, I am using 12 as a constant, 12, and I am going to calculate the effective depth, that is 2400 divided by 12 is equal to 200 mm. Then once if you obtain the depth, we need to calculate the overall depth. So overall depth is equal to effective depth plus effective cover. So I am taking 35 mm as the effective cover. So 200 is the effective depth plus 35 mm. The total is 235. So we are rounding up to 240 mm. So D is 240 mm. So width of the lintel, as we are discussing in the earlier session, the width of the lintel is equal to almost all width of the wall. So that is thickness of the masonry is equal to 30 mm. Then once next step is effective span. As we know, the effective span is equal to the two steps. One is clear span plus half of the bearing on each side, or that is this, or clear span plus effective depth of the lintel. So in this problem, we have clear span is equal to 2.4, bearing is 0.23. So we'll get a 2.63 meter as a first case. Second case, it will be 2.4 clear span plus 0.2 as the effective depth. So total will be 2.6 meter. Therefore, finally, the effective span is equal to 2.6 meters. Once if you obtain the effective span, the next one is load and moment calculation. For transfer of load to the sides by arch action, the condition is that the height of the wall above the lintel, that is h, it should be greater than 1.25 times of h, small h. That is, this h should be greater than 1.25 times of this h, that is the height of the triangle. If in this problem the h given is 3 meter, height of the wall above the lintel is 3 meter. So we need to calculate what is the value of h. Therefore, h is equal to effective span into sine 60. So effective span is 2.6 into sine 60 is equal to 2.25 meters. This we have to compare with the capital H. Before that, we need to calculate 1.25 times of H, that is equal to 2.82 meters. Therefore, if H is greater than 1.25 times of H, we can compare here. This H is 3 meter, that is height of the wall is 3 meter, and this H into 1.25 H is hardly 2.282 meter. Therefore, we can say H is greater than 1.25 times of H. Hence, the imaginary load W is a triangular load. So, the imaginary load is a triangular load. So, how to calculate the triangular load? So, triangular load to obtain, we know the area of the triangle multiplied by the thickness into density. Therefore, 1 by 2 base is effective length, that is LE, into height is LE into sine 60, into thickness is the thickness of the wall, and rho m is the density of the masonry. By knowing all these values, and if you substitute effective length and the density of the material and thickness of the wall, you will get a total weight is equal to 12.93 kilonewton as a triangular load. Once if you obtain the load, we need to calculate the moment due to masonry load, which is acting in the form of triangular load. Therefore, that I am calling it here as a M1. That is equal to W into LE by 6. It is not a UDL. That's why this equation has become W into LE by 6 for the triangular load. So if you substitute the values of W, span, effective span, and this, you will get a moment equal to 5.63603 kilonewton meter. That is from the triangular load. Next, we need also calculate the self-weight of the lintel. So triangular load is already we have calculated. Now I need to calculate the self-weight of the member, that is in the form of UDL. Self-weight of the beam will be in the form of UDL because it is uniform. Therefore, self-weight is equal to breadth of the section, depth of the section multiplied by density of RCC. That is equal to 0.23, 0.24 into 25. That is the density of the material. You will get a total load is equal to 1.38 kilonewton per meter as a UDL. For that, the moment due to self-weight is equal to WD, because it is a UDL. So it is equal to WLE square by 8. So W is become WD. So 1.38 into span, effective span square divided by 8. You get a value of 1.17 kilonewton meter. So once if you obtained both M1 and M2, M1 is related to the load in the form of triangular, and the M2 is the moment with respect to UDL. We can add these two, M1 and M2, will get a total moment is equal to, bending moment equal to 6.733 kilonewton meter. Finally, the ultimate moment is equal to moment multiplied by factor of safety. So factor of safety is 1.5 and the moment is earlier step what we have calculated 6.773 into 1.5, we get a 10.16 kilonewton meter is the ultimate moment which is acting on a lintel. So we need to check the depth, that is step number 5, check for the depth. So to check for the depth, we are going to equating moment of resistance to ultimate moment. So mu is equal to KFCK BD square. Here the K is equal to 0.138 equal to point, or you may take it as a 0.14 because we are using Fy is equal to 415 steel. Therefore, if we substitute, because we require a value of D here, so it will become in under root mu by K FCK B. So mu 10.16 into 10 raised to 6 and K is 0.14, FCK is 20 and the breadth is 230. We'll get depth is equal to 125.60 mm. It maybe you can call as 130. Since D required is 130 but D provided is 200 mm, then I may say that the section is safe or designed with respect to uh, concrete, it is safe. And this can also be compared with respect to directly by substituting all the values K, FCK, B and D what we have assumed, and then that also we can compare with mu with the moment of resistance. If it is less than, if the bending moment is less than the moment of resistance or mu, then we can say it can be designed as a singly reinforced beam. So that also can help us to check the section capacity. We can also do by that method also. So next step is, once the design is safe with respect to the depth required, then we can go for the design of tension reinforcement. So to obtain the design of tension reinforcement, we may equate to mu is equal to T into Z, where T is equal to 0.87 Fy into AST and Z is called as lever arm is equal to D into 1 minus 4 pi AST into FCK into B into D. This equation is already available in the IS 456. So we can use this equation to obtain the value of ASTs. By substituting the value of moment, the Fy, AST is the unknown we need to calculate, and the D is the depth. And if you substitute all the values, and if you simplify this equation will become in the form of quadratic equations. So quadratic equation means ax square plus bx plus c. So we already know how to solve the quadratic equation, that is x equal to minus b plus or minus root of under root of b square minus 4ac divided by 2 into a, where you can see a is equal to 32.57, b is equal to minus 86.65 into 10 raised to 3 and c is equal to 10.16 into 10 raised to 6. If you all substitute in the quadratic equation, you will get a solution that in the form of AST, that AST is equal to 130.24 millimeter square. It is the amount of steel required. So this steel we are going to provide in the form of number of bars by providing 10 mm diameter bars. If we use a 10 mm diameter bar, area of the one bar is equal to 78.5 millimeter square. So number of bars equal to total AST divided by area of one bar. If I substitute this, we will get a value of 1.65, say 2 number of bars we are going to provide. So final answer is reinforcement is in the form of 2 into 2 numbers of 10 mm diameter bars. So depth is 200 mm. Finally, effective depth, then this will be uh, 2 number of reinforcement. So once if you design the flexure, next is design of shear reinforcement. So to design the shear reinforcement, we need to calculate first shear force. So here also we'll have two values. One is with respect to shear force with respect to dead load, shear force with respect to wall above it, that is the triangular load. So half of this triangular load and the total load divided by 2, that is the UDL load by 2, will get in a shear force. So that is the values if you substitute, and we will get the value of shear force. So this may not be ultimate. To make it an ultimate, we will going to multiply with a factor of safety of 1.5. So we will get a total shear force is equal to 12.606 kilonewton. Next step, we need to calculate nominal shear stress or shear stress. So shear stress as per the code tau V is equal to Vu by Vd. So if you substitute in this equation, we are obtaining a stress is equal to 0.23 Newton per millimeter square. This value we need to compare with the value of design shear strength of concrete. That is the strength of the design shear strength of the concrete as a tau C. So to obtain the tau C, first we need to calculate the what is the amount of percentage of steel. So to get a steel, as we already know, the AST provided these two numbers. So we have calculated the total number of bars, area of the tensile reinforcement as 157 millimeter square. Therefore, percentage of steel is equal to 100 AST by BD. Therefore, percentage is equal to 0.28 percentage. With help of this 0.28 percentage and the refer to the table number 19 IS 456 2000, we need to obtain the value of 2C by interpolating. So for 0.25%, we have a tau C is equal to 0.36, and for 0.5 we have a tau C is equal to 0.48, but for 0.28 we need to interpolate. Therefore, for 0.28 we need to calculate. Therefore, tau C is equal to 0.36. That is the interpolation equation. We will get a value of 0.37 Newton per millimeter square as a tau C. Now we need to compare the value of tau C with respect to tau V. Since the tau C is greater than the tau V value, that means shear strength of the concrete is more than the nominal shear strength of the concrete. We entire shear is taken by concrete alone. So we need not to design the shear reinforcement, but as per the codal provisions, we need to provide the nominal shear reinforcement. Therefore, we are assuming a shear reinforcement in the form of stirrups of 6 mm dia bars of having a two-legged stirrups. So the area of one stirrups is equal to 56.55 millimeter square. So this stirrups we need to provide with the spacing. The spacing of the stirrup should be least of the following three conditions. That is SV is equal to 0.87 Fy into ASB into 0.4 into B. Substitute all the values, we'll get a spacing is equal to 221. We may say it is a 220 mm. In second case, it should not be greater than, spacing should not be greater than 0.75 D. That's value is equal to 180 mm. Then third one, SV should not be greater than 300 mm. Out of these three cases, whichever is less, that we will going to provide. Therefore, we are providing 6 mm two-legged stirrups about 180 mm center to center. So once if we design, we need to draw the we have to show the reinforcement details. So main reinforcement is two numbers of 10 mm hash. Hanger bars we are providing, that is two number of 8 mm. Then shear reinforcement 6 mm dia, two-legged about 180 mm center to center spacing. So this is the drawn problem. What they have given as a space as the span and the support, and this is a cross section what we have obtained in the first step of our design. That is 230 mm width and 240 mm depth. And this is the main reinforcement, two numbers of 10 mm hash, and similarly on the cross section. And these are two hanger bars which are providing on the top. So in the cross sections you can see here. Then these are the stirrups which are spaced equally. Here also you can see in the cross sections. Then you can see how to show the stair reinforcement spacing. So one bar to another, one stirrups to another stirrups. So this is 6 mm dia hash about two-legged stirrups. about 180 mm center to center. So this is how we can sketch the reinforcement details what we have designed so far. Next problem. Design of lintel for a width of opening is equal to 2.1 meter. Height of the brick wall above the lintel is 3 meter. Thickness of the wall and bearing is 230 mm and chajja. So in this problem, the chajja is connected to the lintel. So its span is 0.6 meter span and its total load of 5 kilonewton per meter square, including sulfate. That means whatever the live load is there and dead weight is there, by adding all that he has given as a 5 kilonewton per meter square as a including sulfate. And we are using M20 concrete and Fe415 steel, and the weight of the concrete 25 kilonewton and weight of the brick wall as 19.2 kilonewton per meter square cube, and we need to sketch the reinforcement details. So as mentioned, this opening is 2.1 meter and height is once again 3 meter, and the thickness of the wall is 230 mm and bearing also we are taking as a 230 mm, and there is a chajja. So this is what we are calling as a chajja. The span of the chajja is 0.6. That means from here to here, the span is 6 meter. And the total load of this is equal to, including live load and sulfate, all 5 kilonewton per meter square. And we are using FCK 20 Newton per millimeter square and FI is 415 Newton per millimeter square, and density of the concrete, and this is the density of the brick wall. So as we discussed in the earlier problem, is here also same. We are going to calculate the effective depth with respect to L by D ratios. So here I am taking 12 as a ratio, L by D ratio. So it will become 175 mm. We are calculating overall depth by with the help of effective depth plus effective cover. Therefore, D is equal to capital depth. D is equal to 175 plus 30, that is 210 mm. Therefore, overall depth is equal to 210 mm. Once if you design depth, add up the depth by assumption, next we'll go for the width of the lintel. So width of the lintel, as we seen in the earlier problem, it is equal to width of the wall. So width of the wall is equal to 230 mm. Therefore, width of the lintel is also we are keeping equal to the width of the masonry as 230 mm. Then effective span, the two cases, one is clear span plus bearing, clear span plus one bearing or half of the bearing on both sides, then clear span plus effective depth. Therefore, 2.1 plus 0.23 is the bearing, 2.43 first case, second case 2.1 into effective depth 0.175, 2.275 meter. So whichever is the less means effective length equal to 2.275 meters. Then load and moment calculation. So to verify whether it is a triangular load or not, we need to verify the edge and this. We have to compare the value of edge and h 1.25 times of h. So we need to calculate what is the value of h first to become an action. So in this problem, as we know, the effective length h, this height of the triangle is equal to LE into sine 60, that is 2.275 into sine 60 is equal to 1.97 meters, and 1.25 times of h equal to 2.46 meters. So now you can compare this value with this value. So this shows that this is also an h is greater than 1.25 times of h. Therefore, the load, hence the masonry load W is a triangular load. So to get a triangular load, we need to multiply area with the thickness of the wall multiplied by the density of the material. So 1 by 2 into 2.275 into height multiplied by thickness into density, will get a weight is equal to, triangular load weight is equal to 9.89 kilonewton as a masonry load in the form of triangular load. So moment due to masonry load, M1 is equal to WLE by 6. Substitute the value of W and LE, you will get a moment M1 is equal to 0.78 kilonewton meter. Next, we need to also calculate the sulfate of the lintel. So that is the density of the cross-sectional area multiplied by density of the concrete. So we'll get a load equal to sulfate is equal to in the form of UDL as 1.21 kilonewton meter. Then moment due to sulfate, as it is a UDL, so WLE square by 8, W become WD. So we get a value is equal to, substitute the values and get the value of 0.78. Answer will become 0.78 kilonewton meter. Then next one is, as we seen in the problem, it is connected, this lintel is connected with the chajja. Therefore, we should also calculate this load because it is supporting on the, it is resting on this chajja. It is interlinked with the chajja. Chajja is interlinked with the lintel. So we need to transfer this load to the lintel also. Therefore, load from the chajja to transfer, we have to multiply by load into the span of the chajja. That is, load is equal to 5 kilonewton per meter square and the span is 0.6. So it will become 3 kilonewton per meter. So this is also throughout the length of the lintel. That's why we need to calculate the moment due to chajja in the form of UDL. So once if you substitute the value of load in this equation in the form of UDL, we are getting a moment is equal to 1.94 kilonewton per meter. So here we have three values of moments, total bending moment is that is equal to M1 due to low wall over it, and M2 with the sulfate, M3 with respect to chajja. So if we add all these values, we'll get a moment is equal to 6.47 kilonewton meter. But to design, we need a ultimate moment. So ultimate moment is equal to factor of safety multiplied by moment. We will get a moment is equal to 9.705 kilonewton meter as a ultimate moment. Once if you obtain the moment, we need to check for the depth. So equating moment of resistance equal to ultimate moment, we are getting mu is equal to k FCK BD square, and k is equal to 0.14 because Fy is equal to 415. So d required is equal to under root of mu by k FCK BD square, and if you substitute moment constant and FCK and breadth, we are obtaining a value is equal to 130 mm. Therefore, this d required, this is actually small d, this d required is equal to 130 is less than 175 d provided. So the design is safe. Once if a design is safe with respect to depth, we need to provide the tension reinforcement in the tension zone because it can be designed as a singly reinforced beam. So this is a equation that is a T into Z. Z is called as lever arm, T is called as a tensile force. So if you substitute all the values in these above equations, that is a moment, steel, type of steel, or characteristic strength of the steel, area of steel we need to calculate, D is the depth what we have obtained, provided, and once if you calculate this, here also this equation become quadratic. If you solve this quadratic equation in the form of ax square plus bx plus c, where a is equal to 32.57, b is equal to minus 63.18 into 10 to the 3, and c is equal to 9.705 into 10 to the 6. And as we know, x is nothing but here ast. X or ast is equal to minus b plus or minus root of b square minus 4ac whole divided by 2a. Once if you solve that equation, we get our AST is equal to 168.09 millimeter square. So this area of steel we should provide in the form of number of bars. That's why we are adopting 10 mm diameter bars. So area of one bar is equal to 78.5 millimeter square, and the number of bars is equal to total area of the divided by area of one bar. So we are getting 2.14. Therefore, we can provide it in the form of three numbers. So once if you finish the flexure, we also design for the shear reinforcement. So shear force first we need to calculate. As comparing with earlier problem, there we have only these two values. Now we are having extra this because the chejai is connected. So as we know, the chejai is also in UDL. Load from the chejai is also in the form of UDL. Therefore, the shear force is equal to WL by 2. So this is the extra thing we are adding here. So if you substitute all the values with respect to WD span and a W concentrated triangular load, then the load from the Cheja multiplied with the effective span, we divided by 2, you'll get a shear force. Shear force is equal to 9.734 kilonewton. But we need a ultimate shear force. To get ultimate shear force, we need to multiply with the 1.5 as a factor of safety. So we got a value of 14.60 kilonewton. The once if you got a shear force, we need to calculate the shear stress, or you may call it as a nominal shear stress. So nominal shear stress tau V is equal to Vu by Vd. So Vu by Vd, if you substitute the value of Vu, B and D, you'll get a stress is equal to, so nominal shear stress is equal to 0.3 Newton per millimeter square. Next, this value we need to compare with the design shear strength of the concrete. To obtain the design shear strength of the concrete, I need to calculate the percentage of steel. So to get the percentage of steel, we should have already three numbers of bars as provided of flexural reinforcement. So that will equal to 230 total area. So percentage of steel is equal to 100 AST by BD. Substituting the values of all these, will get a percentage of steel as 0.6. With respect to point 0.6, we need to calculate the value of to C from referring the table number 19 IS 456 2000. And since we have a values of 0.5 and we have a value of 0.75, but we need to calculate for 0.6 percentage of steel. That's why we are interpolating. If you interpolate by interpolating equations, we are getting a to C value as 0.51 Newton per millimeter square. Now we are comparing tau C 0.51 Newton per millimeter square with the tau V, that is 0.36 Newton per millimeter square. By comparing these two values, we'll come to know that the strength of the concrete is more, or it can resist the shear stress, that is nominal shear stress. That means we need not to provide the shear, we need not to design the shear reinforcement because the shear is taken by the concrete alone. But still, we need to provide the nominal shear reinforcement as the IS 456 conditions. Nominal shear reinforcement. So to provide a nominal shear reinforcement, we are providing 6 mm diameter bar as a shear reinforcement in the form of stirrups. So the area of the one stirrup is equal to, which is having two-legged stirrups, 56.55, and this can be provided in the form of spacing. So spacing is equal to first equation 0.87 f into ASU by 0.4 times of B. So the answer is equal to 133.70. Here I am replacing Fy in the form of 250 Newton per millimeter square. Because if I provide 415, we are getting a maximum, we are getting a large spacing, but for the other conditions, it may not be satisfying. That's why I am changing the type of the steel as 250 Newton per millimeter square. And here, if you calculate 0.75 times of D, there is another condition of SV, we are getting 127.5. Then if you tow SV should not be greater than 300 mm as per the codal provisions. So finally, lesser of these three things we have to provide. Therefore, provide 6 mm dia mild steel reinforcement in the form of stirrups at a spacing of 125 mm center to center. So once if you design depth, reinforcement with respect to flexure as well as shear, we need to sketch the reinforcement. So reinforcement details, main reinforcement are 3 numbers of 10 mm and hanger bars 2 numbers of 8 mm and shear reinforcement 6 mm dia about 2 legged about 125 mm center to center. Therefore, we can see here, so main reinforcement is provided in the form of 3 numbers and shear hanger bars in the form of this And the stirrups, you can see these are the stirrups which we are providing all around. So they are provided at the spacing of 6 mm dia, two-legged stirrups, about 125 mm center to center. So totally, even you can see in the cross section, three numbers of main reinforcement, two numbers of hanger bars, and a stirrups. And size is 230, depth is 210 mm. So these are the some of the references what I have referred to prepare this content. And I wanted to thanks to all the my uh, chairman, civil board, moderators, and subject experts, and also content all my colleagues who have helped me to develop this content. Thank you.